to go over a problem that is relatively simple. We're just going to look for a tension in a cable, but it's holding back a, well, for lack of a better description, something like a diving board. Okay, so here's how this goes. We have, well, I don't know why I always wind up in red. We're going to do this structure right here. Okay, and we'll do this, and I'm going to put a anchor right here. So we have a pin right there. Okay, we're going to call this A, and over at this end is B, and then we are coming down to an anchor point here that's called C. Okay, and this would be really easy if that's all there was to it. So we're not doing that. We're going to make it complicated. We're going to put a force here at 15 pounds. We're going to put a force here at 20 pounds. And you know what? Here's another lesson I learned years ago as a student too, so I should do it. Try to draw your visuals so that they look like the size of the forces they are. We're going to do another one here, and this will be at 35 pounds. And we're going to do another one here, and this is going to be 20 pounds. And of course we want to have one hanging way out here, and this is 15 pounds. Okay, now we are 6 inches between here, 8 inches between here, 8 inches between there, and 6 inches between there. So that's our dimensions. Now we're going to actually have a cable that holds this back like so. So literally this is the cable of the beam and cable. Alright, so how do we do this? Well, we need to sit down and determine what's going on and figure out what we have. So free body diagram time. So I'm going to draw it like so. Okay, and our first point is right here at A, and we have another one here at B. Alright, and I'm going to switch to red so you can see this, but we're going to have a of X force, and we're going to have a of Y force. Alright, then we are going to have 15 pounds here, and we're going to have our 20 pounds here, and I need to pause for a minute. Alright, let's get back to what we're doing here. Sorry for the interruption. Alright, so we're in the midst of putting forces on here. So we have 35 here. We have 20 here. And we have 15 out at the end. Okay, so there's our forces, and that's our free body diagram with now this one, which will be the tension on this, and we're going to label this one F, B, C. Okay, so in order to find all this, we need to start doing things. Okay, so we're going to write it like this. So find reaction at A in the x-axis. Right? So positive to the right, some of the forces in the X, and basically we're going to find out that A of X is equal to 0. Okay, actually I don't need that in there. There are no other forces acting at that point. So basically this is just a pin with the vertical forces loaded on it. Okay, so that part's easy. All right, find the reactions at A in the Y axis. All right, and with that one, I'm going to cheat. I'm going to start with the sum of the moments bit. All right, because it's a little easier to do that and then solve for the sum of the forces as a check. But basically, remember, sum of the forces in the X, sum of the forces in the Y, and sum of the, let's do that nicely, sum of the moments. Okay, use those three to solve this. But the truth is, I'm going to start with the moments because I'm going to take a moment about point B and figure out what AY is. So I'm going to start over here and work my way left, and that'll leave me, when I'm all said and done, I'll need to figure out what the tension is in BC. So I'm just going to do it this way, and I'm going to make that way positive based on everything that's going on with the forces up above, and we're going to do sum of the moments about point B. Okay, that's going to be equal to 0, and let me bring that back down here. So if I do it about this point right here, that means the 20 is going in the positive direction, the 35 is going in the positive direction, 20, 15. I just know that it's going to work out, that I'll get the answer I'm looking for. But you could assume that counterclockwise or clockwise is always positive instead of going counterclockwise in this one. But as long as you pay attention to your signs, it's not going to change how you do this. Okay, so let me do this problem out for you. So I'm going to take, remember we had 6 inches here, 8 inches there, 8 inches there, and 6 inches there. Okay. All right, so I'm going to write down 15 pounds. I'm going all the way to the left, so that is times 28 inches. Okay, and it's positive because that's the rotation I'm looking at. And if I do 20 pounds, and the next one is going to be 22 inches plus 35 pounds, and that's going to be 14 inches. Okay, and the last two are going to get stretched out here, so I'm going to write them over here. So we're also doing plus 20 pounds, and it's 6 inches minus AY, and that's 6 inches also. Okay, so this was the first force, this is the second force, third force, fifth force. 1, 2, 3, 4, and the fifth is AY. Okay, and basically I'm going to rewrite the equation, and I'm going to assume that you can do the algebra that goes with this, but we're going to do all of this across the top. So let me do it out just to be on the safe side, but I'm going to not talk to you. Okay, so 15 times 28, 20 times 22, 35 times 14, 20 times 6, and all divided by the 6 from the distance of the AY. And when I get done, I'm going to get 245 pounds, and that's positive, is the reaction for that. And if I go all the way over using the comp paper to my advantage, I'll write 245 pounds vertical. Okay, so that's what's going on there. All right, now find the tension in BC. All right, so let's go back here and look at the drawing for a minute. So now I'm going to look for this one right here. So if I take a look at this, I now know AY. I know all these other forces. I can figure this one out. Okay, could do this with some of the forces in the Y, which would be great. Or just to get you used to doing moments again, I'm going to do it with the sum of the moments. But now we're going to take the sum of the moments about A. Okay, and I'm going to keep the same counterclockwise positive. Alright, set it equal to 0. We're going to do 15 pounds. Now, we're about A, so that means our distance has changed. So there's now 22 inches to the left, plus 20 pounds, 16 inches to the left of A, plus 35 pounds, and that's 8 inches to the left of A, minus 15 pounds at 6 inches, minus FBC at 6 inches. Okay, so that accounts for all the forces. So take some time here with yourself and look at these numbers and see how I did that. So when I did the moment about A, I account for everything that's left and right of A. Okay, and notice that the 20 pounds at A does not affect the moment of this beam. Okay, so if it's acting at the point, you can neglect it. That's why we're taking it about A. So we get to get rid of that one and we get rid of the AY. So the 20 pounds there, and this go, if you like putting it down, think of it as 20 pounds times 0 inches, which means it's a 0, so it doesn't exist. Okay. So when we're all said and done, we're going to do the same thing. So FBC works out. I'll let you do the math, but basically I'm dividing everything in the numerator by 6 inches once I move FBC to the left, and we're going to get 140 pounds in tension. Okay. Now here's a chance to use all this for checks. If you're not sure you did it right, let's do it this way. So positive up, we're going to do sum of the forces in the Y equal to 0 equal to minus 15 minus 20 minus 35 pounds minus 20 pounds plus 245 pounds minus 15 minus 140, and write the units down there, be consistent. And if we get all said and done, it should be equal to 0. And check, we did this problem correctly. Okay, it's as simple as that. And most equilibrium problems in statics are of this nature. Okay, you can use any of these three in any way to help you get to a solution. Most of the time you're going to have to do some of the moments to actually get to that. But then you check back with some of the forces in the X and Y direction. Okay, cool.